Hey, this is Dr. B, and let's try a couple of equilibrium problems. In this first problem, we have some substance X combining with Y to form Z in the ratio of 1 to 1 to 2. Since this is an equilibrium problem, I'm already thinking that KEQ will be equal to Z squared over X times Y. Nothing gets eliminated, no solids or liquids. When 4 moles each of X and Y, so those are my initial conditions for X and Y, no Z yet, are put in a 1-liter vessel. That means the concentration is 4 molar. After all, molarity is moles per liter. And allowed to react, it hits equilibrium, and you end up with 6 moles of Z. So the change for Z is from 0 to 6. However, it'll only be half for X and Y, because for every molecule of Z that forms, only one molecule of Y goes away and one molecule of X, giving me equilibrium concentrations of 4 minus 3, or 1 for X, 4 minus 3 and 1 for Y, and 6 for Z. Since it's squared, KEQ will be 6 squared over 1 times 1. The answer is going to be 36. That's doing it in your head. Let's do it using an ice table. Draw your ice table and lay out your chemical reaction. Fine. Write in those initial concentrations that they gave you. No Z yet. Determine the change based on what they told you occurs at equilibrium. If it's going from 0 to 6 for Z, that's an increase of 6. And only 3 of Y will go away, and only 3 of X will go away by virtue of the 1 to 1 to 2 ratio. Filling out the chart, we can see that we have values of 1, 1, and 6 for each of the reactants and products respectively. Setting up the expression, the equilibrium constant will be equal to 6 squared, since coefficients become exponent, over 1, and 36, a nice healthy equilibrium constant. Another problem. Phosgene decomposes into carbon monoxide and chlorine. Just like we did before, I'm thinking it's going to be equal to this times this, carbon monoxide times chlorine over the phosgene, with a nice 1 to 1 to 1 ratio, and nothing is omitted. The flask initially is at 1 atmosphere. Don't be put off by the atmospheres. It's analogous to concentration. So that means we'll have 1 and 0, 0 for the initial conditions. And what do they tell us happens at equilibrium? The temperature we don't worry about. As long as it's constant, we will get a nice value there. And when it's done at equilibrium, the total pressure is 1.2. Now that's different. I can't say what this turns into. I can't say what this turns into. I can't say what that turns into. We'll have to use generic X's to represent each one. So let's go ahead and go directly, in this case, to our ice table. Phosgene turning into carbon monoxide and chlorine. They do tell us that's at 1 atmosphere, so we must not have any of the two products. We can't say specifically what the change is. We can't even say specifically what's happening at equilibrium. So let's just say that the phosgene is definitely going to get partially consumed, so it's going down by a value of X. And hey, just like we did with numbers, if this goes down by a value X, each of those go up by the same value. Well, that's nice. Let's go ahead and sum it up. Now, here's the key point. What is the total pressure due to? Those three things. The total pressure is the sum of the partial pressures. So very, very important for these summation type problems, write that the total equals 1.2. If you do that, you've actually set up how to solve for X. And just like I just said, the partial pressures become the total pressure when you sum them up. So there it is, writing it again, which you don't really even have to, but what is X going to be equal? Well, I see a minus X and a plus X. Let's get rid of that. 1 plus X equals 1.2. X is 0.2. Now, some people redraw an entire ice table, but let's not do that. Let's just simply notice that this bottom value is going to be 1 minus 0.2. There it is. X is 0.2. 1 minus 0.2. And then the two top numbers will each be 0.2. So the equilibrium constant will be 0.2 squared divided by 0.8, which is 0.05, which is not a very strong equilibrium constant. These are two sample equilibrium problems.